Jai Hind to all of you. My name is Dr. Ritish Kumar and I am going to give a lecture on the subject electronic devices, and the topic is Fermi Dirac distribution and PN junction. So let's begin the topics. So this one is showing the university syllabus of the course, that is electronic devices, and the subject code is BEC 301, and this course is totally uh, uh, totally categorized in 5 units: the first, second, third, and fourth, and fifth. As you can see, the first unit is totally related to the semiconductor physics, where we will study about the quantum mechanics, and second unit is totally related to the intrinsic and extrinsic silicon, where we will learn about the diffusion process and drift process, and apart from that, drift current and diffusion current. And third unit is related to the PN junction diode characteristics, IV characteristics, Zener breakdown, avalanche breakdown, etc. And fourth unit is totally related to the bipolar junction transistor, that is BJT. And fifth unit is related to the field effect transistor, that is FET, where we have different kind of configurations such as common source, common drain, and common gate, and all these kind of topics we will learn in this subject, that is electronic devices. So these are the text and references books, and I will prefer the first two books, that is Benjamin Streetman and Banerjee, and the second book is Neiman and Donald. So I will prefer these two text and references books for this electronic devices subject. So let's begin. The topic is Fermi Dirac distribution. So as you can see, Fermi Dirac distribution, as the name suggested, it gives the information of distribution of electron within the certain levels. So the levels are nothing but the energy levels, as you can see. So we can able to find out the concentrations of the carriers such as electrons and holes within the certain energy levels. So as you can see, the distribution of carriers within the certain energy level is called Fermi Dirac distribution. So it has some formula for the distribution of electron over a range of allowed energy levels at thermal equilibrium is given by, as you can see, this is the Fermi Dirac distribution formula, where you can see it is denoted by Fe, and the formula is 1 upon 1 plus e to the power e minus ef upon kT, where kT is the thermal voltage, and you can also write it BT as well, and EF is the energy level, and EF is the Fermi energy level. So where we have some constant, that is K. This constant is known as Boltzmann constant, as you all are aware about the Boltzmann constant. The value of Boltzmann constant is 8.62 in 10 to the power minus 5 for the unit of electron volt per Kelvin, while for joule per Kelvin it has the value of 1.38 into 10 to the power minus 23. These two values you are need to remember, because in the question paper it can possible that you don't have the values in the question, so you need to remember these two values. The next is now I would like to explore this Fermi Dirac distribution function. Uh, so the Fermi Dirac distribution function again, it gives the probability that an available energy state at E will be occupied by an electron at absolute temperature T. The quantity of Fermi levels so you can see at E is equal to EF, what should be the probability to have the electrons at the energy level of Fermi level. So you can put E is equal to EF in this equation, then you will get the value of 1 upon 1 plus 1, that is equal to half, that is nothing but the 50% filled states. So we can say thus an energy state at the Fermi level has a probability of 50% of being occupied by an electron. So this is the another definition of the Fermi level, where we have the probability of electron is equal to the 50%. So this is the distribution of Fermi level. So where we have specified the term Fermi probability function versus energy for different temperatures. So I have plotted, or I have given the diagram for different distribution function for different temperatures. As you can see, at T is equal to 0, so as we know, Fe is equal to 1 upon 1 plus e to the power e minus ef upon kt. So as you can see, at t is equal to 0, this value will become e to the power infinity, and 1 upon infinity is equal to 0. Right? So the analysis of this Fe is not complete by putting t is equal to 0 only here. So here we have considered two cases. The first case, for t is equal to 0, you need to consider two cases. The first case, where we need to consider E is greater than EF, right? If E is greater than EF, this value should be greater than 0, right? Should be greater than 0. Then you will have the value of Fe is equal to 0. While for E is less than equal to EF, then this quantity will become negative. Then you will have 1 upon 1 plus e to the power minus infinity, that is equal to Fe is equal to 1 by doing the analysis of this equation. So you can see for t is equal to 0, we have two cases. For E is greater than EF, we have the value equal to 0, while E is less than equal to EF, it has the value equal to 1. While talking about E is equal to at EF, what should be the value? So at E is equal to EF, this value should become equal to 0. 1 plus e to the power 0, that is 1 upon 1 plus 1, that is half. So for this case, Fe is equal to half, that is 50%. That you can see here, at E is equal to EF, the value of distribution is exactly equal to the half. So at every temperature values, at E is equal to EF, the value of occupied or probability of electrons is always equal to the half. That's why it passes through the half it passes through the half probability functions, as you can clearly observe here, right? So as you increase the temperature beyond the T is equal to 0, as you can see. So in other words, firstly, before starting to increase the temperature, I need to explain one thing. uh, E is equal to, if E is greater than EF, the probability is equal to 0. That means it is a totally empty state, right? If I ask, if I say E is less than equal to EF, it has the probability of having the electron is 1. That is it is a totally filled state, right? So if you increase the temperature beyond 0 degree, then you will have some filled state at E is greater than EF. So this one is the filled state, you can see, and corresponding to this filled state, you will have some this empty state here. So these are the filled state at T is equal to T1, which is greater than 0. If you increase the temperature again more than T1, then you will have the more filled state at E at energy level greater than Fermi energy level, and corresponding to these field state, you will have some empty state below the Fermi energy level. That is the concept of Fermi Dirac distribution functions here. So this is all about the Fermi Dirac distribution. Ideally, we can say the Fermi Dirac distribution has the rectangular function, while when you increase the temperature, then the Fermi Dirac distribution having some kind of parabolic natures, you can see here. Now these are the explanation of the Fermi Dirac distribution function, as I discussed in the last slides. So next, this diagram is showing the Fermi Dirac distribution for intrinsic semiconductor, N-type semiconductor, and P-type semiconductor. So you can see here, this is the condition for intrinsic semiconductor, where we have the energy level, that is valence band energy level, conduction band energy level, and at a dotted line is showing the Fermi energy level in all the types of material. If you see, for the N-type material, again we have EC, EV, and EF. Again EC, EV, and EF. The dotted line is showing the Fermi level distribution, or Fermi energy level. So you can observe here, for the intrinsic semiconductor, the Fermi level is totally lie in the middle of EC and EV, right? Exactly midpoint, or exactly we can say in the middle of the forbidden gap. And in the case of N-type, you can clearly observe here, the Fermi level is just below the conduction band, while in the case of P-type semiconductor, you can see here the Fermi level is lie just above the valence band, right? So this is the ideal nature of intrinsic semiconductor energy level, N-type semiconductor, and P-type semiconductor. And if you see, if you draw the Fermi Dirac distribution of all these kind of material, then you will have these kind of distribution function, as I discussed in the last slides. If I ask the concentrations levels of the carriers, so you can clearly observe here, for intrinsic semiconductor, the carrier concentration of electrons and holes always be equal for the case of intrinsic. So you can clearly observe here, the quantity of carrier concentration in this diagram is making equal, right? So we can say the concentration of electrons will always be equal to the concentration of hole for the case of intrinsic semiconductor. While in the case of n-type semiconductor, you can see the Fermi level is just lie below the conduction band. Apart from that, you can clearly observe where the concentration of electron is very greater than the concentration of holes here, right? Similarly, you can see for the case of p-type semiconductor, the concentration of holes should be very greater than the concentration of electrons. So this is all about the uh, energy level distribution, electron and hole concentration, that is carrier concentrations of different kind of materials, that is intrinsic, n-type and p-type semiconductors. So I hope this energy band diagram is clear to all of you. The next is junction properties. So as you all are aware about the PN junction, that is nothing but diode. So for making the junction, you need to have two types of semiconductor material, that is p type and n type. So as we already know the energy band diagram for p type and n type, so I have drawn the energy band diagram here, and you can see here for the p-type semiconductor, the Fermi energy level is lie just above the valence band, while in the case of n-type semiconductor, the Fermi level lies just below the conduction band. While making the junction, this Fermi level is making the uniformly distributed over the entire device. So you can see this Fermi level is making a single Fermi level within the device, and due to making the single Fermi level, this energy goes down, means the p-type n-type semiconductors energies goes down. So it makes a barrier in between the junction. As you can see, this barrier is known as contact potential. It is defined by V naught here, and the energy of this contact potential, that is defined by QV naught here. And if I say what should be the electric field direction for the PN junction diode, so you can see here for the n type, we in the depletion layer we have the positive charge, and in the p type case we have the negative charge, that is in other terms we can say these are the acceptor ions and the positives are the donor ions. So electric field always lie from plus to negative direction. So the electric field direction is towards the plus to negative here, right? So these arrow is showing the diffusion process and drift process. So here in the p-type semiconductor, majority carrier is holes. For n-type semiconductor, the majority carriers are electrons, right? So as we know the diffusion process, in the diffusion process the carriers migrate from higher concentration to lower concentrations. So holes will move from p-type to n-type semiconductor. That's why the direction is given, the flow of particles from p to n, because the current should be in the for the whole current should be in the same direction. That's why the current and flow of particles should be in the same direction. While talking about the electron moves from n type to p type semiconductor uh, from the diffusion process. So you can see in the diffusion process the electron movement is from n to p, because the current should be in the opposite direction of the flow of electron. That's why the current direction is opposite in the case of electron. So these the direction flow diagram you can clearly understand by looking this diagram here. So these are the energy band diagram for junction PN junction diode here. So I hope this how it comes, how it generates is clear to all of you. Next, I will discuss two cases, the forward bias and reverse bias. As you know, if you apply the forward bias condition for the PN junction diode and reverse bias condition for the PN junction diode. So in the case of forward bias junction, we know the depletion layer width will decrease and the barrier potential height is also decreased by the amount of BF. So initially without biasing, it has the barrier height V0. By applying the forward bias condition, this barrier height is reduced by the amount of minus VF. While in the case of reverse bias, this barrier height will increase by the amount of BR, right? So this is the reduction in the barrier height by using the forward bias condition and reverse bias condition, and these are the energy band diagram for different cases. So without biasing, it has the barrier contact potential looking like this and reduced by V0 minus VF and increased by V0 plus VR. So these are the energy band diagram for two biasing condition, that is forward bias condition and reverse bias condition. So and these diagram is showing the direction of flow direction of particle flow and the direction of current for different biasing conditions here, as I discussed in the previous slide, and it is clear to understand by looking this diagram. So I hope this one is clear to all of you, and this one is the IV characteristic of simple junction diode. So this region is called as the forward bias condition. Why? Because P is connected to positive and is connected to negative, and this one region is the reverse bias region because P is connected to negative and N is connected to positive. So this is the forward bias characteristics and this one is the reverse bias characteristics. And reverse bias region, we have two different kind of breakdown. We can see the breakdown, the Zener breakdown and avalanche breakdown. So this is the mainly IV characteristic of simple normal diode we have by studying the PN junction diode. So in today's lecture, so we have covered the topic of Fermi Dirac distributions, and we have seen the energy band diagram for different kind of materials such as N-type, P-type and intrinsic material. And apart from that, we have also discussed about the PN junction diode with the energy band diagrams as well. And at last, we have seen the IV characteristics of PN junction diode. So I hope these topics are clear to all of you. Thank you.